Hello, everyone. Welcome to another live stream. This is Q&A about history of science and technology. And for a change, I actually have some live humans here with me because we're at the annual Wolfram Summer School, where we have lots of talented people studying all sorts of interesting things and doing each one doing an original project. This is my moment in the year when I'd get to do my extreme professoring of coming up with lots of projects, both for our grown-up summer school and for our high school summer research program. But okay, so a different experience for me because there's actually people here in person. But I see a number of questions that were saved up on over the last week or so. I see one from Savvy asking, this is one of these questions which seems like a simple question, so maybe I can answer it easily. Asking, under the right circumstances, is it possible that Pompeii could have survived the volcano? Did they have early detection methods back then? It's my impression, and I think it was even described by Pliny the Younger, I think, who wrote about that eruption, that it was one of these things where there were sort of splurts of stuff happening from this volcano for a while before the thing really blew up. And I think this is a really common thing. It's a thing that's kind of weird in the historical record. People say, oh, there was this natural disaster and it was such a problem. But then you discover that there were sort of precursors of the natural disaster, and people viewed it as a tourist attraction to see the things that were sort of the precursors of the natural disaster. I know, for example, another famous case for an engineering situation was the Tacoma Narrows Bridge, which was a suspension bridge in Washington State, where famously, it's in many physics textbooks, it had a roadway that was, when the wind was going past the roadway at a certain speed, the eddies that form behind the roadway caused the roadway to oscillate at a certain frequency. And when the wind was going at a certain speed, that would be the resonant frequency of the roadway. And you could see in the final video of the thing collapsing, the roadway was twisting like crazy. But the thing that was sort of a footnote to that was it had become kind of a tourist attraction to come and see that roadway twisting when the wind was happening. So I think it's in terms of modern times, there's been sort of there are these questions about earthquakes, earthquake detection in many places now. There are the seismic waves travel significantly more slowly than electricity travels in wires, and more slowly than the speed of light for microwave connections. So it's kind of like there's an earthquake coming is something that has been possible to detect in modern times. Certainly was not possible in whatever it was, 79 AD or something, when Pompeii was buried. Let's see, I have a bunch of other questions here from Mouse. What's something funny, odd, or unexpected you've learnt about a famous scientist while researching them? I don't know. One of the things that I'm reminded of is Ludwig Boltzmann, pioneer of statistical mechanics in the 19th century. He was kind of a first principles kind of guy. And when he lived in, I think it was in Vienna, maybe, or maybe in some city in Austria, he was a professor there. And he decided as a first principles guy that he wanted to get good fresh milk for his children. And so he decided to buy a cow. Well, it was, turns out, as an esteemed physicist, his knowledge did not extend to how to keep a cow and how to get a cow so it would produce milk and things like this. So he was asking some professor of zoology at the university how to do this. But apparently there was a moment when Boltzmann was sort of leading this cow through the streets of this town, creating kind of an exotic situation. Actually, talking of people like that, there's almost anybody that one studies, there will be sort of exotic personal details to them. I mean, I think another person actually more directly in the biology zone was a chap called Darcy Wentworth Thompson, who was a person who was sort of famous for bringing some mathematics into biology. He wrote this book called On Growth and Form. He wrote the first edition in 1917, the second edition in 1942. strangely aligning with the First World War and the Second World War, neither of which he was involved in because he was too old, even in the First World War, to be involved. But the most famous page of that book is one where he's showing pictures of fish. And he shows that if you deform a fish by some mathematical transformation, you go from one species of fish to another species of fish. It's a slightly strange claim because the fact is that you have to distort these fish in quite different ways to get from one species to another. But I did find out about him actually from a biography of him written by his daughter that this whole idea of sort of studying different biological forms had come from kind of a Christmas entertainment for children that he had, which was to draw a picture of a dog on a rubber sheet and then pull the rubber sheet in different directions to have it go from one kind of dog to another. But actually, Darcy Wentworth Thompson was quite a character. I mean, he had been he was sort of a classical scholar as well as a biological scholar, and he has, for example, in addition to his book on growth and form, he also has a book of Greek fishes and Greek birds, I think, where he was trying to solve the problem of how do you connect the thing that was described in the Odyssey with some particular name to the thing that we now describe as an eagle or something like this. And so he was trying to figure out those kinds of things. But he also got involved in all sorts of, he got involved in the fisheries board, I think. And he was also a person who was sent to unravel a bunch of issues associated with the Aleutian Islands and Alaska at a time, I think it was right around the time that Russia sold Alaska to the US. And there were all kinds of claims about things going on, and he went out there as a sort of explorer, and there are pictures of him with sleds and dogs and things going to study these kinds of things alongside his kind of efforts at mathematical biology. But I mean, there are, any one of these characters one studies, there are all sorts of things you find. I mean, I did quite a study of Ada Lovelace a while ago, and she was there's lots of exotic stories with her, but I was kind of it was nice to see some of her quite Victorian writing and things like when she got stuck on a problem. She was like, I'm really stuck on this particular thing, she writes in some letter, and they were exchanging letters. The postal service was pretty good in those days. And so I think in London, where she lived, she was exchanging letters with Charles Babbage. And at that time, there were 14 postal deliveries per day in those parts of London. So it was really very much, email style communication. But she's, I think, at a slightly different time, not in the middle of, I think not when she was in the middle of London. She was like, I'm stuck on this problem. I'm going to go off and ride my horse around to kind of clear my head. But it's rather a nice kind of, most of the time, people these days doing science, I think in most places do not go off and ride horses around their properties to relax, so to speak. I'm reminded so many of these stories. I mean, there are almost any character you can ask about there. If I research them in any detail, there are all sorts of interesting personal stories about them, and maybe people can ask about particular people. Let's see. So I'm saying this partly to the folks who are actually here in person. This is a history of science Q&A. So questions about other things we save to another time. Let's see. Well, there are questions here about Lazy asks, how often do historians develop contradictory beliefs based off the same evidence? How do we decide who is right? Well, there are, if you think about things like political history, there are often, multiple different accounts of the exact same thing. I mean, the one that is particularly obvious to somebody like me, having grown up in England and now living in the US, is something like what in the US is called the American Revolution, in England is called the American War of Independence. And there are different accounts of sort of what was going on. Even sometimes there are different accounts of who won, who lost. what does it mean? I mean, I think the issue is always, as it is in so many things, if you ask, oh, if somebody says this side won, the other side lost, you could say that about all sorts of wars and other kinds of things. But, just the definition of words is not necessarily what's important. I mean, if somebody signed a surrender document, okay, then they probably lost. If it was a more complicated thing, you have to sort of ask, so what was the consequence of the conclusion that they lost? And then you can start to have reasonable things to say. But there are questions about there are questions where there's sort of a matter of opinion. Did this person figure this thing out? That's a very common history of science kind of issue. Somebody will say, oh, but really, this thing was figured out by somebody, 500 years earlier. And the question is that really true? And the answer ends up typically being complicated, because typically what happens in a situation like that is that you can read what somebody wrote 500 years earlier. It's written in terms that are very different from the terms one would use today. And a lot of the question of did they figure it out comes in the translation from what they wrote to what we now think about today. So it's almost unanswerable. Did they figure it out? You could imagine going back and talking to them and sort of probing them with questions. And most of the time, those questions, I think they'll be just responding with, I don't know what you're talking about. You could go back and ask, I don't know, let's say Isaac Newton. Did he understand that did he understand the concept of I don't know, the derivative and the integral were inverses, something that we consider sort of standard in calculus today. And was that, I mean, how well did he understand that? I'm not sure that term of things being inverses and so on, he wouldn't really have been a thing he would have understood, because he was formulating everything in geometrical terms. So it's kind of like, well, did this line intersect that line? It's a different kind of question. So I think it's sometimes these things end up just being sort of unanswerable, or depending on what you mean by the question you're asking. Let's see. So Ching asks, I've always been fascinated by the ages of people of interest throughout history of science when they make their key contributions. Some of them were remarkably young. It's a funny thing. There's kind of this myth that sort of advances in science are always made by the young. This myth appears, I mean, insofar as I've looked at this appears to be a myth. It doesn't appear to be true. And there are a few comments to make. I think some part of that sort of story came from a particular thing that was written by G.H. Hardy, wrote a book called A Mathematician's Apology, which is a funny book. I mean, it's partly a book about sort of what it means to do mathematics. It's partly kind of a personal book. I think the edition that one most commonly sees has a foreword by Freeman Dyson, who's a person I knew for quite a number of years. But G.H. Hardy had this statement, oh, people do math productively when they're young, and they're all washed up when they're older. Well, the truth is, G.H. Hardy was all washed up when he was older and had a whole sort of kind of what I think we would now say is sort of a depressive story about the whole thing. But the evidence that sort of math is done by the young isn't really there. I mean, for G.H. Hardy, it was true, and G.H. Hardy was around in the early part of the 20th century in Cambridge. Probably the thing for which he is most famous is sort of the discovery of Ramanujan. Ramanujan was an Indian mathematician who was quite young and who'd been decently educated in India, but was by the time he was then a clerk at the port of Madras. Being a clerk, one of the important things was being able to do arithmetic very well. And he was able to do arithmetic very well. He was a very good calculator. He applied his calculation not only to tallying up kind of shipping receipts and so on, which apparently he did in a very short amount of time during the day, but applying those skills to sort of studying questions in number theory and so on. and his sort of prowess in doing calculations led him to all sorts of experimental mathematics kinds of conclusions. And he wrote these letters to various people, wrote to another mathematician named Neville, and then he wrote a letter to G.H. Hardy saying, here are a bunch of mathematical results, and what do you think of these? And there are a lot of exotic results. There are a lot of very strange things that are relations between numbers and series and so on. And G.H. Hardy had the good sense to sort of come to the conclusion that these, well, he checked a few of them and was like, these are so bizarre and surprising that even the ones that he couldn't immediately check, he sort of, his scientific induction said, those are probably right too. That wasn't actually necessarily the right thing to conclude. But anyway, he was responsible for sort of discovering Ramanujan, bringing him to Cambridge. I don't think Ramanujan had a very good time in Cambridge and unfortunately died fairly soon thereafter. But one of the things with G.H. Hardy was G.H. Hardy, I think, will have been completely mystified by Ramanujan and how Ramanujan was producing these sort of remarkable mathematical results that he was. I mean, I think the true situation was Ramanujan was a very good calculator and was good at doing sort of experimental mathematics and had good intuition about mathematics. So when he could see some particular phenomenon from his calculations, he could generalize it and come to a mathematical conclusion when other people would just have said, oh, it's a coincidence that e to the pi square root of 173 is roughly an integer and so on. But he turned that into something real, which in that particular case became sort of a good method for computing the value of pi for a long time. But to Hardy, he was sort of asking Ramanujan, but how do you prove these things that you have derived? And because to Hardy, that was how you do mathematics. You produce, you go step by step, you prove things, that's how you conclude what's true, as opposed to the sort of experimental method that Ramanujan was using. And I think at some point, Ramanujan got sufficiently frustrated with the whole thing that Ramanujan had something of a sense of humor. He said to Hardy, oh, I come up with these things because some Indian goddess tells me about them in when I'm asleep. And so Hardy sort of, repeated that in a very kind of straight way. I'm pretty sure that was kind of a joke. And it was kind of like, stop asking me how I prove these things, because I'm not finding these things by making proofs in the kind of way that Hardy did it. And I think this led Hardy, is one of the things that led Hardy to be convinced that he was kind of all washed up and would not be able to do sort of more mathematics again, and came up with the global conclusion that because he was not able to do mathematics when he was older, nor could anybody else. Okay, so having said that, I think that's the origin of that story. But if you look at the actuality of people and when they discover things, yes, there are young folk who've discovered things and discovered significant things. I tend to think that the way it works is that all of us have at most one kind of big sort of paradigmatic idea about how to think about things. And if your big paradigmatic idea is something that happens to kind of be immediately applicable, you can discover things even when you're quite young. And perhaps, but that paradigmatic idea sort of keeps going. I mean, in my own case, sort of the paradigmatic idea that I've been pursuing for the last 45 years has to do with thinking about things in computational terms. And I've been lucky or something that paradigmatic idea has been a very powerful one that has indeed been able to let one figure out a lot of kinds of things. And I happened to start doing science when I was pretty young. I started off doing things like particle physics in a very sort of traditional way. But by the time I was, I guess, 21 years old or so, I was doing this kind of computational explorations methodology and finding all kinds of interesting results. But once, that methodology was one that happened to come naturally to me for various reasons, and then was able to start sort of picking the fruit even at a pretty young age. What you see in other cases, I mean, there are lots of great contributions that have been made by quite young people. Another example is Évariste Galois, in 1830s, I guess, 1820s maybe, who came up with the basic ideas for group theory. Monsieur Galois, I think, was a young fellow, late teens, I guess, being well educated in France. He was also quite a political activist, which was not a did not increase life expectancy in those years, and he ended up doing a bunch of interesting work in group theory, which I think was I think he really did do that work. I think it was somewhat amplified by people who were on sort of the same side as him in the political activism business. I mean, he died at the age of 21, I think, eventually in a duel, but that was sort of a put-up job that was the result of kind of political factions and so on that he was involved in. But he's an example of somebody where the contributions he made when he was young because he died very young. I mean, there are plenty of other examples of, I mean, it's sort of a selection effect as well among some scientists and mathematicians of old, because life expectancies were shorter. So it's kind of like if you were going to make a contribution, if you died at the age of 35, and we know about you today, it's kind of inevitable that your contribution was made when you were young. Now, it has to be said, when you start looking at these things, I mean, lots of people, I don't know, Isaac Newton, how old was he when he was doing Principia Mathematica? Well, let's see, he was born in 1642, and Principia Mathematica was 1687. So that means he was, 45. Did I get that arithmetic right? Yeah, I think so. By the time he was doing his great work, so that I don't think that counts as being completely young. I think it's really a myth. I think if you plot sort of when did people do their sort of most famous work, it's a pretty uniform distribution across ages. I know Benoit Mandelbrot, inventor of fractals, who I knew, although he didn't like me very much for various reasons. But Benoit always was very frustrated with people when he was older, when he was getting into his 70s and 80s and so on. He was very frustrated with this claim that sort of this myth that all good science is done by the young. And what he used to say is sort of big science that integrates lots of different areas, he claimed was usually done by older folk, because you just have to know a bunch of different things for one to be able to sort of do these integrative kinds of things. I'm not sure if that is entirely correct, but there's certainly that's a reasonable hypothesis. I think what tends to happen in science is there's science where there's sort of one point thing you discover, and it doesn't require a big tower to be built to get to that one point thing. It needs a paradigmatic advance, but then the fruit is hanging right there, easy to get. Then there are other things where you need to build a big tower to get to the thing that you might discover. Maybe that big tower is something that involves doing experiments, and you have to build up some whole complicated experimental apparatus. Maybe you need a theoretical apparatus to do these things. Those things don't happen quickly. Those things happen, decade is sort of the minimum time to build one of those towers typically. And I think there are different kinds of advances in science that sort of happen. Some are built on the basis of these sort of big paradigmatic towers. Some are like, oh, we happen to discover this thing. By the way, whenever people say, oh, somebody noticed this thing and they made their big discovery in a day, this is never true. This is, at least in all the cases I've looked at, many, many cases, what you find is, yes, there may be that moment when, the apocryphal apple fell on Isaac Newton's head or something, but it was not the case that before that time, he had never thought about gravity and how gravity works. And then suddenly, the apple falls and suddenly gravity becomes clear to him. No, not at all. There was typically a decade of work at least, sort of getting to the point where you are ready to understand something, which you might understand in the end quickly, but there's a whole sort of pre-development that's necessary to get to the point where you're kind of thinking about things in the right way, that you can make that kind of sudden discovery. I mean, I think in my own case, I've seen a bunch of things I've discovered where I can very clearly see that because I know, for example, in things I discovered about how simple programs produce very complicated behavior, I actually had made simple programs that produce complicated behavior back in 1973, a full, basically, decade before I really noticed that phenomenon. And this is again what people were asking about, sort of kind of how you understand the historical record and so on. And I think that's a case where you could say, well, did you discover these things back in 1973? Well, not really. I had I had a computer calculation that showed the phenomenon, but I didn't know what I was looking at. And so I couldn't really say that was the thing I discovered at that time. It was a thing that was something that, well, it happened to be there, but it wasn't something that I had sort of internalized and quotes discovered. So I think it was for me, it took sort of developing the kind of conceptual framework to think about how simple programs behave and to kind of sort of turn over various other rocks and realize that other things weren't what was going on and there really was something new happening. That took for me basically about a decade. And that's a very typical thing that you see in the history of science, that even though, I can say June 1st, 1984 was when I really first paid attention to Rule 30, it was that was the result of something that had sort of been developing for a decade or so. Let's see. It's a question from Tarek here. What commonalities do you see among the most impactful scientists? I think the one theme is it's the what question do you ask is more important than how do you answer the question. It's the in the practicality of it is that many more people learn the mechanics of how to answer questions than are good at formulating what question they should ask. And it's really common to see that once you've formulated the question clearly, you're a significant part of the way towards answering the question. And usually the sort of most, I would say, paradigmatically impactful scientists, and there are slightly different kinds of scientific progress that get made. Sometimes people build these sort of big paradigms that involve thinking about things in very different kinds of ways, and sometimes people are more sort of building methods to sort of do things within an existing paradigm and just inventing sort of strategies for making progress within that existing paradigm. But I think that this whole question of sort of the strategy of what you study and maybe sometimes how you study it is by far the dominant effect in the ultimate impact of what scientists do. It's, I mean, there will be, even in cases where sort of the main accomplishment seems to be that, excuse me, even when it seems like the main accomplishment is solving some existing problem, like, proving Fermat's last theorem or something like this. The real things that were done were strategic things about sort of building up this kind of new way to solve a problem like that, rather than the pure mechanics of solving the problem. I think that's one thing. Another thing that usually helps is sort of the exposition of what was going on. When somebody sort of, quote, solves the problem, but nobody can understand what they did, that doesn't usually help. And what's happened, in history of science recently, there's been a tremendous trend for people to say, well, this thing that used to be called the Friedman universe should be called the Friedman-Robertson-Walker universe and the Friedman-Robertson-Walker-Lemaitre universe and so on. There are sort of names that get added. That particular one, I have not studied the details of what was originally done, but my guess is, maybe unfair to Monsieur Lemaitre, that once you know the answer, you go back and see that other people were sort of close to the answer, but their exposition was not understood. It may be quite unfair in that particular case, but there's been quite a trend in recent times of sort of adding names to concepts, sort of based on the fact that if you go back and look at it, given what you understand today, you can see more of, you can see that the seeds were there. But I think in terms of sort of okay, so when we talk about impact of scientists, there are a couple of complicated things. One thing is, did the impact happen immediately, or did it happen 50, 100 or more years later? And I think when it's going to happen immediately, there has to be some expositional sort of effectiveness to the whole thing. For example, with Charles Darwin, the fact that Origin of Species was a quite readable book that came on the heels of a bunch of quite popular sort of travel books that Darwin had written, that really helped in the impact that came from those ideas. Um, I think yeah, that to me, the dominant effect is always sort of this strategy of what question do you study. Um, and um, let's see. Hal comments, we think of robotics and automation as modern inventions, but ancient Greeks had things like wine pouring automata, vending machines, water clocks. Why do you think this is rarely taught? You know, when you say vending machine, that is a very modern concept. And I don't know exactly what the ancient Greeks had, but I bet it didn't look like a modern vending machine where you put coins in it. It's you know, this is a typical example, I think, of where, you know, you can see something that we have in today's world and you can back project it to something that existed in antiquity and say, well, you know, they had this, they didn't have it. For example, the Antikythera device, this kind of clockwork cog-based thing from around 0 AD, was you know, it was a computer of a certain kind. Should we really say that it was the invention of the computer? I'm not sure. It was a thing for doing a sort of a more slide rule type thing for doing, although it had many cogs, for doing calculations, astronomical kinds of calculations. Um, it's and the question of why people don't hear about these things more. Sometimes what was really there was something quite obscure and hard to understand what it really did. I mean, for example, you go, you see the remains of water clocks. You know, I've seen these things. It's like there's a spout, there's a this, there's a that. How did this thing really work? You know, is it clear how it really worked? It's also complicated because there will be comments about how things work that are in various kinds of writers from antiquity. Very little work has survived from antiquity. But for example, people will now interpret Cicero as having said that were things that we now might be like the Antikythera device. But you know, taking that one sentence, I don't know quite what it was, about sort of ways to calculate things and deducing from that that this thing was like a computer and so on would not really be a correct inference. I mean, I think that there's a whole question of automation and machinery in ancient times. And I mean, the truth was there was a lot of human labor available in ancient times. You know, maybe not always gotten in the best way, so to speak, but there was lots of human labor available. So lots of kinds of things that it makes sense now to automate. It's just you have a person do that. The one place where there was a whole bunch of technology in antiquity was war machines. All kinds of things like you built a bunch of walls around your city, and then you want to, you know, you want to sort of attack the city. Well, you need this big siege machine that's going to come and, you know, build a big tower, or you need catapults that are going to fling things over the city walls, things like that. And so a lot of ancient inventions were really around things for waging war. They were not around sort of everyday kinds of things, because the everyday kinds of things that people needed, there were people who could do those things. At least that's my impression. So and when we hear about things like catapults, for example, you know, I think one does hear about those kinds of things. There weren't you know, lots of everyday inventions. I think were a much less common thing. Let's see. Uh, Ellie says there are many reasonably popular books, movies, and plays about the history of math and science. Why do you think there's an abiding cultural interest in content about mathematicians and scientists, but less cultural interest in actually doing math and science? Well, I think at some level, humans like stories about humans. And it's much easier, in a sense, to be sort of telling a story about a human than it is to be sort of describing the intellectual structure that got built. I mean, I think if one were to look at sort of the total number of books about math is much greater than the total number of books about history of math, for example. But when it comes to things like movies, let's say, it's movies are really ultimately driven by stories, and stories tend to be about people and or people like things. And I think I've certainly noticed there are movies I've even had some peripheral involvement in some cases that are sort of historical movies about sort of historical things in math and science. And really in the end, the better movies tend to be the movies that have the better stories, even if the stories are not historically accurate. I mean, I think there are two movies that came out roughly around the same time. One about Alan Turing called The Imitation Game, another about Stephen Hawking. Having known Stephen Hawking and known people who were portrayed in that movie, I would say that movie was a pretty accurate movie historically. The Alan Turing movie was a historically horribly inaccurate movie, but nevertheless, in many ways, it was a better movie. It had a better sort of story arc. Maybe it had details of acting and so on that were better too. But it was sort of an interesting comparison of two movies at about the same time, where sort of the better movie told the better story, even though the better story wasn't the historical story, so to speak. I think when it comes to it's an interesting question whether sort of math and science can be told through personal stories. There's a famous collection of books. I think it's by Eric Temple Bell, and I think rather not really for modern times. I think it's called Men of Mathematics, which but let's assume it was called People of Mathematics. The but it's a collection of stories about well-known mathematicians. Those stories are very I would say they're very impressionistic and they're positive and impressionistic. They're not, again, it doesn't hew that closely to the sort of historical reality. But I think, and the question is, can you learn mathematics by learning the histories of people and so on? I'm not sure. I mean, in some areas, another interesting question about sort of the history of science, sometimes when ideas emerge, when they emerge, they're very clear. And, when you read the original paper, you say, yep, I get what's going on. And when you read sometimes the accounts that people wrote sort of 2 or 3 steps away from the original paper, it's like, oh, this is really hard to understand. I mean, I know for myself, something that I found kind of amusing is there are things that I wrote about, I don't know, 40 years ago or something now, that are now in textbooks. And I read the textbook description and I can't understand it. So this is now maybe that's a sort of a bias of the fact that I had written the original thing, and so I could sort of understand what I'd originally written. But I tend to think that sometimes the original is clearer than what comes later, partly because people often so they want to make it more sort of formal and structured, and I'm not sure, or they're just not as good at explaining the thing, and the person who understood it originally really did understand it, which was how they came to invent it. So sometimes sort of the original is better than what comes later. Sometimes the original is kind of utterly obscure to understand, and partly because people will, gradually develop ideas. I mean, for example, one person I knew quite well. I'm talking about history and names. A person called David Finkelstein, who's a very great contributor to mathematical physics, greater than he's acknowledged to be. But I read his works and so on, and I talked to him, and I'm very confused by his works. He told me one sentence, one fact that really helped me understand his works. He says, well, I've had many different ideas, and sometimes a new idea will contradict an old idea, but I never mention that when I write up the new idea. And so that meant that, you're reading all these papers and books and so on, and it's like, how do these fit together? Well, the answer is they don't, because they were sort of restatements of new ideas that were incompatible with the previous ones. And so, if you were trying to learn sort of those ideas, that will be a very bad situation to try and learn those ideas. And I think, for me, once I think I understand some field, one of the things that I often do is to go back and try and understand the history as a way to be sure that I really understand the field. Somewhat more, I might say obnoxiously, sometimes I think that I figured something out and it's sort of not compatible with the conventional wisdom in that field, and I'm pretty sure I'm right, but I kind of want to know, how do people come to think the thing that is the conventional wisdom? And so then you have to really go back and look at the history and see, why did they think that? And sometimes you say, well, they thought that because they made this mistake in this way at this time. I mean, a particular example of that, notable for our physics project, is this idea of space-time, the idea that space and time are kind of the same sort of thing, which, when Einstein was inventing relativity in 1905 and so on, he didn't really say that. He was like, well, there's this correspondence between space and time and this way in which they're sort of fungible into each other, but he didn't really sort of say they're the same kind of thing. That idea was an idea of Hermann Minkowski's, I think in maybe 1909 or so. And what happened was Minkowski was a number theorist. He'd been studying quadratic forms, sums of numbers, x squared plus y squared, et cetera, et cetera, et cetera. And he looked at the mathematical formula that comes up in relativity of x squared minus c squared t squared. He says, that's a wonderful thing. That's a quadratic form. Let's think of it in that way, in which we're thinking of x and t as just variables that are somehow interchangeable. And that's kind of, I think, how the concept of space-time and the idea that space and time are really the same kind of thing got born. But now understanding that was the origin of that idea, you say, well, that wasn't really the point. So it's not like there's some deep iceberg of thinking that shows that space and time are the same kind of thing. It was just sort of a mathematical trick that turned out to work in an elegant way and was noticed by a particular person at that time. So it helps one in being sure that being confident to say, okay, I'm pretty sure these are different. Let's build a theory based on that difference, rather than worrying that you missed something, that there was an iceberg of history that you somehow missed. Let's see. Nail asks, which nearly forgotten technologist or theorem, if it had caught on sooner, would have changed the modern world the most? I'm pretty sure the answer to that is things about computation. And people like Leibniz, late 1600s, were pretty close to the idea of universal computation. They were pretty close to the idea that you could build sort of a single machine that, if fed the right input, could be made to do any computation. Leibniz was a formalizer trying to sort of figure out how could you represent kind of things in more and more formal ways. I mean, he'd written his PhD thesis on resolving legal arguments using logic, trying to apply sort of the formalistic mechanism of logic to, in that particular case, the law, but he went on and tried to sort of formalize many other kinds of things. I sometimes wondered whether he'd invented a Turing machine back in 1690 or something. A decade or more ago, I went and looked at his archive and so on, just to flip through the papers and just see, did I notice a picture of a Turing machine there? Because actually, again, these are things written in Latin, and it's not easy to interpret. If you'd seen some diagram with a bunch of lines and squiggles and so on, it's like, what is this thing? Now, with sort of modern understanding, you might be able to go back and see what that was. I have to say, in looking through archives, many times I have seen what might have appeared to people as doodles, but because I know about certain things or have worked certain things out myself, I can recognize, yes, that's a picture of a sorting network or something, even though in the actual archive, it's a piece of paper with a bunch of lines and a bunch of lines on it. That's the thing you can understand. And so I was curious, did Leibniz actually come up with this idea, but maybe not stated in a way that anybody understood, or that even he himself deeply understood? So that's an example of something which was sort of, I think, a near miss. That idea really did emerge in the 1840s with with Ada Lovelace and Charles Babbage and so on, but particularly Ada Lovelace, this idea of universal computation. At the time, there was really a near miss in history because Charles Babbage had developed these mechanical computers and so on, and was really mostly concerned with making things like mathematical tables automatically, or as he put it, by steam, because steam was the sort of the main method of automation in those days. So he was really, can we make mathematical tables? The French, or as the competitors at the time, he had found were, Napoleon had started some whole program of making mathematical tables by hand, and he wanted to automate that and make the British win, so to speak. But and he built these mechanical computers for doing that. Ada Lovelace, who saw herself mainly as sort of an expositor of what was going on, was, I think, the first person who really realized with clarity that you could make you could use kind of the thing. Babbage had this idea of an analytical engine, which he thought of as a way to compute table of logarithms, table of squares, table of reciprocals, and so on. I think Ada understood with much more clarity that if you could build this, you could sort of make it compute anything, as she put it, can weave algebraical patterns as the Jacquard loom weaves pictures of birds and flowers and so on. So, she had that idea, and Babbage was obsessed with trying to get the British government to pay for his machines to be built. One of the things that I think I discovered looking through the historical record is throughout his life, Babbage was convinced that Ada Lovelace was much wealthier than he was, because Ada Lovelace was, countess and married to a person who was a lord and so on and so on and so on, and it was a higher station in the social hierarchy, and he was convinced she was much richer than he was. His father, Babbage's father, had been a banker who had left him a lot of money. And I'm pretty sure that Babbage was actually wealthier than Ada, but he never knew it in his life. But anyway, Babbage was always trying to convince the British government to put up money for his machines, and he was pretty inept at doing that. And he kind of was did lots of things that didn't endear him to the government and so on, though they did put up some money for his machines. But at some point, Ada basically wrote to Babbage and said, "Look, just let me, Ada, basically be the CEO of this operation, and you do the CTO type thing." And at first, you see in the letter, Babbage says, writes on the letter, rejected all her demands. But then it becomes clear that, a week later, he'd said, "Yeah, that's a pretty good idea." Unfortunately, Ada got sick with cancer, and really was sort of a downhill story from then on, and so this never happened. Had it happened, there would have been a Victorian mechanical computer cloud computing service, probably. I mean, the analytical engine would have been the size of a locomotive, powered by steam. Although there were electrical people, there were the Faraday and the electrical folk were around, and they did know those people. So maybe they would have had an electrical version of the analytical engine, but more likely they would have had this giant steam-powered, deeply steampunk thing and their concept was to have people send in calculations, whether it was calculations for artillery, for example, for the trajectories of shells and so on, whether it was calculations for life insurance tables. Babbage had been involved in a life insurance startup, or other kinds of things. The concept was people would send in their calculations and then they would be done on the analytical engine. And so we might have had cloud computing in the 1840s, albeit with a very big, clanking steam-powered thing. So that's and as it was, the sort of it took the development of electronics, first, actually not just electromechanical devices, but actual electronics with vacuum tubes and so on, before one had actual electronic computers in the 1940s. And I think that could have happened much earlier with different and more Victorian technology, so to speak. Let's see. Let's see. Demario is asking, let's see, there are many questions here. I'm going to, well, okay. There's one from Lucas here. What are the key factors that attract people to science? Is that environmental, people are just born for it, a mix between them, or what? Well, I think in part, the the kind of societal environment leads people to do science or not to do science. I mean, for example, for myself, I grew up in the 1960s when space was a big thing and when it was kind of that was sort of the vision of the future was things happening in space, and that was technology, and that was sort of related to science. Uh, when I was growing up in England, scientists were not viewed in particularly high regard. I mean, they were typically referred to in the popular press as boffins, and they were typically portrayed as having white coats and things like this, and being rather they were not portrayed in a very positive light. But nevertheless, things like the space program was sort of driving the technology as a cool thing. I mean, there are different times in history when people you can really very clearly see kind of societal pressures or societal values leading people to science or not to science, so to speak. I mean, I think in ancient Greece, for example, sort of there were lots of people who liked to talk about philosophy, and that sort of led to a bunch of writing about natural science. People sort of thought that was a thing worth talking about. I think less so in the Roman times. There was less, it was much more like let's go to war and conquer a country rather than let's ponder the philosophy of how things work. If you go to more modern times, I would say that the kind of the interest in things like mathematics. I mean, mathematics have been invented in, as far as we know, in places like ancient Babylon, first for commercial transactions, for accounting, and second of all for things like land surveying. That was sort of the origin of geometry, and then for construction of pyramids and things like this. But these were, the interest in mathematics was at that time, well, I think was largely driven by these practical commercial kinds of things. And for a long time, mathematics was a commercial activity. I mean, there was sort of another branch of the sort of Babylonian story was astronomy, where sort of the big issue was let's predict the future. And there were kind of astrologers who were trying to predict the future by looking at the bones of sheep and the entrails of goats and things like this. And they were sort of interestingly at the time, there were three types of things they were trying to predict. They were trying to predict sort of their test case was, where's that planet going to be at this time in the future? Because you could check that. Another thing you could do, which you could also check, was, is it going to rain tomorrow or not? Another thing you could do is predict, who's going to win or lose this battle. Well, turned out the astrologers were trying to do all three of these things. Turned out the first one was sort of doable by mathematics, and the second one, predicting whether it's going to rain tomorrow, well, we're pretty close to that now, 2,500 years later. And who's going to win or lose that battle? Well, we don't really have a scientific theory of that even today, and not clear that such a theory is possible. But I think in the so, at that time, sort of the should you be a mathematician? It's like, well, if you were a merchant, if you were an accountant, if you were doing accounting, then sure, you should learn mathematics. And when people like Fibonacci in the early 1200s were writing books about, Liber Abaci, for example, his big book, the Book of the Abacus, which contains his famous Fibonacci sequence, when he was doing that, mathematics was for merchants. And people were going around teaching merchants how to do mathematics better. It then became the case in the 1400s that mathematics became kind of a spectator sport, different from today. I mean, people would do things like say, I can demonstrate the solutions to the cubic equation, and I will do it at court at such and such a time. And there would be these competitions between people. There was lots of skullduggery associated with that. But that was kind of, mathematics as sport, mathematics as sort of, I can prove how clever I am by doing mathematics as a piece of entertainment, so to speak. The sort of the mathematics that then the big thing that happened in the 1600s was this kind of merger of mathematics that had come from things like accounting and so on with the question of how do we understand the natural world. And that's why, famously, Newton's book, Principia Mathematica, its full title is Mathematical Principles of Natural Philosophy. So it's kind of the idea is we've got natural philosophy, we've been thinking about how the world works. Now we're going to bring mathematics into that story of how the world works. And I think the question of what, at that time, what was pulling people into mathematics, I think there were some drivers. I mean, there were things like, well, another thing that brought people into mathematics was music. From the time of the Pythagoreans, there was sort of this idea that music was associated with kind of ratios of numbers and so on. People knew that from lengths of strings and tones that they produced, things like that. I think that, but I mean, this question of what really brings people into science, what has brought people into science, that there are lots of different waves. For example, in biology, natural history, that became a big pastime in places like England in the 19th century, and that 18th century to 19th century. People were collecting all these weird things, and I think it was also a time when there was still some exploration of the world going on, and that meant that people were going to Patagonia and coming back with this strange kind of turtle or something, and that was kind of a driver for that sort of science. And there were people who were doing science because they were sort of collectors of things. Maybe they were also explorers and so on. I think in more recent times, there have been sort of different drivers of people going into science. I mean, well, there've been, for example, after World War II, in the US, for example, the Manhattan Project had been a big sort of military success, and that drove a lot of kind of government interest in science and physics and so on. But I think it didn't really take off until Sputnik, 1957, when the US sort of said, oh my gosh, there aren't enough people who know about science in this country. Let's go develop things and encourage more people to get involved with science. Now, you'll see in different parts of the world, different kinds of things happening. For example, in the Soviet Union, where, if you were going to be an intellectual and you were going to be an intellectual who wrote about the humanities, you might end up in hot water because the things you would write would somehow be inconsistent with the regime, et cetera, et cetera, et cetera. But it was pretty safe to work on mathematics or physics for that matter. That was a place, and so you see an awful lot of work done in the Soviet Union by people who were, you're going to be an intellectual. What kind of intellectual are you going to be? The safe kind of intellectual is to be a mathematician or a physicist. And that drove a lot of kind of interest and people into that area. I mean, I would say at different times, there are things like in today's world, lots of people sort of are pulled into certain areas that I don't know, lots of people being pulled into finance, for example, lots of people being pulled into the tech industry. These are things which are somehow adjacent to various scientific questions, but certainly don't directly lead to that. So I think and in terms of individual people, you hear from most people who do science, they'll say, well, actually, I got pretty interested in this most of the time. They'll say they got interested in it around middle school type age, around, early tween type age. I think that's I don't know, I think that's just a feature of how people work, that you kind of, that's the point at which you kind of can start to have your own views about what you should be doing. And some people, it lands on science and some it does not. There's certainly the having ambient sort of science things, being exposed to science, knowing anything about the fact that science is a thing is obviously necessary, or at least very useful. And I don't know, there are all kinds of other forces, you might say. Are there television programs about science? Are there museums associated with science? Are there classes about science in school? I mean, one thing that happens with classes in school is sometimes that's a double-edged sword, because if you take this science which somebody might be really excited about, and you turn it into this very mechanical thing that is sort of processable by the school system, people might say, yeah, I thought I was interested in that stuff, but it's really very dry. I don't really care about it. And you lose those people. And sometimes things happen, for example, in mathematics. There are people, this is sort of one of the mistakes sometimes in mathematics education, even at the college level, is the math courses are too hard. And so people who are sort of fundamentally interested in mathematical kinds of things, they're sort of dry, difficult courses, and they're like, I guess this isn't for me. And those people are lost to that kind of area. Let's see. Um, Willem asks, how do you think future scientists will look back at your work? And is that something you care about or think about? It's not something one has a lot of control over. I think the thing that the thing that's sort of a strange thing for me is that I've been doing sciencey things for 50 years now, and so I can kind of see a little bit of the arc of what happens and how ideas get absorbed. And sometimes things happen quickly, but often it takes shockingly long. And sometimes the really confusing thing is that right after you introduce some idea, there is immediate pickup of some kind. And you think, oh, okay, we're on a good track. This is going to get absorbed quickly. But no, decades go by, and that first, puff of absorption, that was all well and good, but the deeper absorption is just still going decades later. I think, I've been lucky, I suppose, in having worked on a bunch of sort of paradigmatic ideas that I think are absolutely fated to be sort of central ideas in the future. And that's, perhaps more a matter of the luck of the time when I started working on these things and the tools that I had, which admittedly in many cases I built myself. But it's something where there's a certain inexorability to some of these kinds of things. That computation will be a significant paradigm for thinking about things, everything is sort of inexorable. I mean, I kind of knew that from the early 80s, and by 20 years later, yes, people were saying, I mean, in early times, people had said, no, 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 we don't need mathematical formulas. They're the way we describe the world precisely. But nowadays, most new models that get made in terms of programs, which is kind of what I had thought would be the case and said would be the case. But that took maybe 25, 30 years or something to happen. There are other things where the timescales are really pretty long. And it's interesting to see sometimes there are things. One thing that happens is things that one thinks are kind of trivial. People say, oh, that's really cool. I'm not sure that's a permanent effect. I think sometimes those are the things that sort of happen quickly that people say, oh, that's really a cool thing. We're going to pursue it now. And the things which are really the deeper things take those 50 years or whatever it is to develop. So I think it's one of these things where you do what you do. I do what I do mostly because I think it's interesting. And also it's very addictive in a sense. Once you realize, oh, I can figure out some foundational thing, and then you see, gosh, now I built this tower of ideas. Now I can look out from this tower and I can see another really interesting thing. It's a very addictive thing. You just go chasing these successive things that you can figure out. And I've been doing that now for about 50 years. So that's something which one is doing for oneself at the time one is doing it. My point of view is, for me, the more significant thing is that I find it fun to just spread these ideas because I like the concept that other people will have fun thinking about these ideas. I mean, I guess everybody has different forms of fulfillment. That's one for me, for whatever reason. I find sort of it's a kind of, I get sort of a warm and fuzzy feeling when I think that these ideas that I've had, which I think are pretty cool, that other people will look at them and say, hey, I think that's cool too. And they'll have that same feeling. That to me is a valuable thing. And for me, sort of getting ideas out in a form that has the clarity necessary for them to be absorbed widely, that's the main effect there. If it's something where sort of the what happens in the distant future, it's like that's not of immediate concern. The immediate concern is what happens now. Let's see. Damario asks, I mentioned the story of Newton getting hit by an apple, leading to his theory of gravity. Have I had a similar experience? What was it? What was the outcome? Oh gosh, I've had that experience many times. I mean, as I say, there's always this long buildup of, how do you think about things and et cetera, et cetera, et cetera. And then, there'll be a particular idea, like for example, the idea of using hypergraphs as a foundation for thinking about the structure of space and so on. I had that idea in 2018. I was driving from somewhere to somewhere and thinking about these things, and I had that idea. Definite time. And then, I started writing programs, and within an hour or so, I kind of had the basic outline of what was going on. But that was the result of what was it, 30 years earlier. I had started thinking about what might space be, what might the underlying structure of space be. Oh, I thought about it in terms of graphs. I ran into some technical difficulties with graphs, which actually, had I known what I now know about hypergraphs, those technical difficulties were kind of silly. They were not relevant. I didn't need to get worried about those technical difficulties, but I did. And so, that was a sort of example of that. I think that sometimes it's I mean, as I say, you just have to, there's a lot of priming. Once you've had that priming, sometimes an actual discovery is a sudden thing that for me is most commonly comes about because I do some computer experiment and gosh, it works in this way, which is usually not the way I expected it to work. Let's see, Iobo asks, tell us how scientists collaborate with big projects for decades. Do you need to know the project history to contribute? Well, I don't know. There are organized collaborations of scientists, particularly in areas like physics, where doing that experiment that involves building a particle accelerator or a giant telescope or sending something into space, costs hundreds of millions of dollars, and it's sort of inevitable that that ends up being a huge effort that involves hundreds of people. And those collaborations, usually they're like little companies, and in some cases, not very little companies with a certain amount of investment money. And then the buildup of the whole thing takes, it takes a decade to build the equipment, takes more time to do this and that. Those things are quite structured, and people often stay with those projects for a long time, not least because if you were 25 years old and you got involved with some project to go try and discover some particular thing like gravitational waves, let's say. I mean, I knew the people who were starting to study the possibility of detecting gravitational waves. I knew those people in the late 1970s, and it took until the 2010s before that experiment really paid off. And at least some of those people had kind of been part of that effort throughout that long period of time. And if you want to see the results, you kind of have to stick around. As far as the general sort of notion of collaboration in science and the fact that science is the result of many hands contributing to things, I think sometimes that's a complicated story because often it's harder for a collective group to have innovative ideas than for individual people to have innovative ideas. In fact, sometimes the presence of that whole group kind of drags things down and makes things more likely to not be innovative. So, when you look at the history of science, a lot of the time, it's individual contributions of individual people that really are the things that really move the needle. I think in different areas that works a little differently. I mean, sometimes a certain fraction of the effort is kind of incremental progress where sort of many small contributions really add up to something. And in other cases, it's really just this moment of paradigmatic change that's the thing that kind of moves things forward. And I think when it comes to different fields of science, there are fields of science where there's sort of a clique of people that work sort of together and they're sort of friends, they're sort of enemies, they're sort of competing, they're sort of collaborating, and that can happen throughout their careers. I mean, there are fields of science, usually when the fields of science are comparatively small, I think they're often, it's complicated. They're sometimes more collegial when they're quite small. I know, for example, the field of general relativity, studying sort of features of gravity according to Einstein's general theory of relativity. That was a field that was quite small through the 1960s, 1970s, even into the 1980s. A field that, at least from my point of view, somewhat from the outside, I was sort of peripherally involved in it, seemed like a very congenial kind of field where people knew each other and they were all sort of contributing and helping each other and so on. There are other fields like particle physics in the late 1970s was a field where, suddenly the fruit orchard was opened and there was a lot of low-hanging fruit to be picked. And it was a deeply competitive field where people were like, am I going to publish this paper this week or next week? Or am I going to get scooped by this group or that group? I think in the end, most of those kind of scoopings didn't really add up to very much. But at the time, it felt very kind of cutthroat and competitive. And while you could say that there were lots of people contributing to progress at that time, it certainly wasn't in the nature of it sort of was collaborative, but it was sort of competitive as well. And I think that's, it varies with the field. There are different fields that work differently. And I think this idea that there are big projects that kind of move fields forward is a complicated one. I mean, to give you examples, Human Genome Project. Well, there were just, Craig Venter had a key idea. There were small numbers of people who were really pushing that. It was something which, in the end, I guess, involved just a lot of machinery, but I don't think it really involved a lot of sort of a scientific collaboration between a lot of people. In different areas of science, people sort of sometimes think, well, let's have a big science version of this. The most common reason for wanting a big science version of a thing is because that's an excuse to get a bunch of money from the government, for example, to do that thing. So, for example, in modern times, there's been a little bit of a push for sort of big math, where people say, let's try and formalize sort of all the theorems of mathematics or in some area of mathematics so that we can deal with them computationally. It's something I worked on maybe 15 years ago or so now, sort of decided that it wasn't really what mathematicians quite wanted, though I thought it was an interesting thing to do. But it's now something where people are saying, let's aggregate that. Let's make a sort of a big math effort where it makes sense to put lots of money into that effort. It's kind of at some level, it's driven by sort of grantsmanship and financial considerations. Let's see. Demario is saying, I talked about these movies about various scientists and asking if there was a movie ever made about me, what actor would I choose to play me? Well, first of all, if the movie was any good, I can guarantee that I would have no choice in this. Second of all, I'm not sure the movie would be any good because I'm not sure that there are stories that are great movie-like stories, and there are stories that really aren't. And I think there has to be more drama, and I think that in some cases the some part of my efforts in life are to have a certain amount of intellectual drama, but as little non-intellectual drama as possible. And I think for example, in the Alan Turing movie that I mentioned earlier, there was drama injected into the movie which wasn't there in real life, and I think that's so it's a complicated thing. Let's see. Entropy is asking, very appropriately, was Boltzmann really tormented by entropy to the point of madness? Okay, so I have looked into this story in some detail. I mean, Boltzmann was a kind of got off to a perfectly good start in physics, and he sort of got this idea that one should take seriously the molecular theory of gases, that gases are made of discrete molecules, and that you could calculate things on that basis and so on. And he developed a long way in that direction. But people didn't really believe him. And people didn't really think. They said, gases aren't made of molecules. There's discreteness isn't a thing. Just as people might today say, discreteness of space isn't a thing. In the 19th century, people were saying discreteness of matter isn't a thing. And Boltzmann, in fact, part of what happened was that Boltzmann said, well, we can't see molecules, but we can see their effects. And that whole idea of there's a thing that you sort of ontologically, it's sort of a strange ontological thing. We can't pick up the thing and show it, but we can kind of see its effects. And partly through that, Boltzmann ended up getting quite involved in philosophy. In fact, in his later life, he was even a professor of philosophy, and he wrote many things about kind of the philosophy of science and whether a thing can be a thing without being something you can pick up and see. That same kind of debate came up again with quarks, where, well, there are quarks, but they're permanently confined inside things like protons. What sense did it make to say they were a thing that exists? Boltzmann got to writing about that as a philosophical matter later in his life. Now, Boltzmann also, by the time he was in his 30s, I think, was having these bouts of what he called neurasthenia, I think, which I think today we would think of as bipolar disorder or something like this. But Boltzmann was having these kind of psychological episodes, and he was having things where he just didn't feel like doing anything, and those got sort of worse and worse. And that, meanwhile, I mean, he was in many ways a rather cheerful fellow. I think and he was quite funny, and particularly he did a visit to the U.S. in 1906, I think, and he went to Berkeley and other places, and he has some great. He talks about he had a little article, maybe even a book that he wrote about something about a German professor visits America type thing, and it's full of fun things. Like he says, I think these Americans have a good chance of doing something interesting, although I saw them at their worst doing integrals and things. And so he was a very, he had a sort of cheerful travel log that he wrote. Well, by the next year, he was in the middle of some depression, and he'd also independently, he'd kind of, on the molecular theory, he'd kind of pushed it very hard, and eventually he kind of concluded, he wrote a book about the kinetic theory of gases, and he pretty much said, that's it, I'm done with this. And he had some quote that says, about molecular theory, he says, one man cannot turn the tide of history, but I'm at least going to write down what I have to say about the kinetic theory of gases so that when this is all thought about later, this can be rediscovered, so to speak, and people won't have to start from scratch. So he was like, people didn't really believe him, weren't really interested. And then I think, when was it? I think maybe I may have my date slightly off, 1908, maybe, I'm not sure. But anyway, Boltzmann was, he was married. He had, I think, 3 daughters, maybe. And they were sort of, as a cheer up old Ludwig, he went off to vacation in Italy, and I guess and hanged himself. But it's not, I think the dominant effect was a pure internal psychological effect. The dominant effect wasn't the lack of people being convinced about the molecular theory. And at least based on the writings that he had, that was, he was perfectly cheerful, if somewhat jaded and cynical about the whole thing. But that wasn't, I think it was a sort of an internal problem. I think that, and certainly one wouldn't have said that he was mad in the sense of, the things he wrote were, even if he was down, he wasn't saying sort of crazy things. It is an irony of history that Boltzmann, if he had been able to trawl the literature well enough, would have discovered that Brownian motion had been discovered. The idea that you look in a microscope, you look at little pollen grains, and you can see them being discretely kicked by something if they're suspended on water, and those discrete kicks are molecules hitting the pollen grains and moving them. And that's something that was discovered in 1827 by a botanist called Robert Brown. But Boltzmann didn't know about that. That only entered the mathematical physics world with Smoluchowski and then with Einstein around eventually with Einstein in 1905. Smoluchowski, I think, was 1900. In 1905, that was kind of the realization that, yes, you could really think of Brownian motion was sort of evidence for the discreteness of matter. Actually, it's interesting the extent to which Einstein really based his thinking on Boltzmann. Boltzmann had been a kind of a physicist who thought philosophically about things, and that was very important in kind of Einstein's formulation of in 1905 of special relativity, Brownian motion, and the photoelectric effect. All, well, certainly the photoelectric effect and Brownian motion were very influenced by Boltzmann. And for example, the photoelectric effect, which was the discovery of basically the idea of photons, clarifying that light could be thought of as discrete, that was something that Boltzmann had actually thought of, discrete energies. And he'd actually, as a matter of mathematical calculation, he had worked things out on the basis of energy being discrete. But he said, but this is just a mathematical trick. This is not something that will be a matter of physical reality. And so it was Einstein who then sort of said, well, actually, let's take that more seriously. Planck before him had also made use of Boltzmann's formulas in this for blackbody radiation and so on. Let's see. I should a few of these. Let's see. Tarek is asking, will the future of science be more led by people who know how to organize and lead groups of scientists, like the kinds of things I try to do, rather than individual contributors in history like Newton, Einstein, Leibniz, and so on? You know, I used to think, I was kind of 30 years ago, 40 years ago, I used to think when you imagine what was the life environment of a typical scientist, at that time, it was like the life environment of a scientist was they were a professor somewhere. For a couple of hundred years, that was the typical life environment of a scientist. Before that time, there weren't really so much professors. There were rare cases where people were professors, like Newton, for example. But more often, they were people who were, you know, court scientists, for example, or maybe they were private individuals who were sort of gentleman scientists or whatever. It was only, you know, and by the time we got to the 19th century, there were professional scientists who were typically professors. And I had always thought that sort of in the future, sort of every scientist one had heard of, so to speak, would have been running, you know, would have had a company rather than having rather than being a professor at a university. That may still come to pass. I mean, the big issue, which is sort of the big elephant in the room, is how should society support basic research? Why should society support basic research? And sort of the mechanism for supporting basic research in a country like the US has been most predominantly sort of universities whose main mission was originally teaching, but they wanted to have people who kind of knew their subjects well, and that was a thing that you got by sort of doing research in those subjects. And then that the government was kind of wanted to just, particularly after Sputnik, wanted to kind of just make sure there was science capability in the country and potentially science advances in the country, and was doing that by giving money to universities. And then that was kind of and so therefore the place you were, if you wanted to be a basic scientist, you were ultimately going to be supported pretty much by the government or by sort of the day job of doing teaching, that then, you know, a university was the place to be. Now, you know, if there were different mechanisms for supporting basic research, if it turned out that we finally figured out how to use, you know, some tokenization blockchain mechanism for being able to support basic research today when the results will come 200 years later or something, if that got figured out, then this idea that you should merge sort of basic research with universities wouldn't be there. I mean, in countries other than the US, things work a little bit differently, and sometimes basic research isn't done to such a large extent. I mean, the thing to realize about basic research is, from a sort of purely economic point of view, I think the time when basic research makes the most sense to support is when the entity that's supporting it kind of has a monopoly on the uses of that basic research. I mean, insofar as the US is the largest economy, it makes sense that anything that is invented that creates economic value is going to most importantly kind of come back to the US, so to speak. if you're a company that has, I don't know, the like Bell Labs in its heyday when the phone system, it had sort of a monopoly on the phones, on the US phone system, that was a time when it made sense to do essentially basic research of a kind that was vaguely in the direction of telecommunications or transistors or whatever else, because the giant distribution channel for all that technology was through the phone system. So but in times when sort of there are lots of competing entities, if you do basic research and you put it out in the world, other than looking cool by doing that and maybe being able to get investors who say you must be cool because you're doing all this basic research, it doesn't really, it's not going to benefit you because all your competitors who are sort of right in there with you are going to be able to take advantage of it as well. So it's a difficult thing to know sort of how basic research should be done. And sometimes people say, well, get all these companies to collaborate. And even though they're competing, get them to collaborate on the basic research. That usually leads to entities that are so steeped in sort of bureaucracy to do with keeping the warring factions at peace, so to speak, that that isn't very successful. Let's see, a few more minutes. Pietro says, many advances related to science and technology were motivated or pushed by world events like the Industrial Revolution, world wars, and so on. How do you think this might happen in the future? It will absolutely happen in the future. I mean, it is the, people, I don't know, it must be a feature of our species, so to speak, that, when there are no forcing functions, people just hang out. And, well, I mean, I guess I don't know the history of ancient Athens well enough, but one has the impression that no, I mean there was, when people were sort of philosophizing, there were wars going on at the same time. So I don't know exactly what that dynamic was, but it's certainly the lesson of history in more recent times has been very clearly that inventions get made when they need to get made, and the two forces at work. One is inventions get made when they need to get made, and the other is when people are in the middle of some disastrous war or something like that. They're off doing that, and they're not thinking thoughts about foundations of mathematics or something of that kind. So I think it's sort of a double-edged thing. There are some things that best happen, are not, the world has to not be pushing too hard. Now, there are other things like it's very important, I think, that there are sort of these aspirations that develop. Like the space program is a good example of an aspiration, and people are trying to repeat that today with the, go to Mars or whatever else. Those aspirations may very well if handled correctly, deliver sort of a runoff of lots of scientific advances. Whether kind of, I think those are typical things. I mean, I think the other thing to realize is that ambient technology is usually very important for the progress of science. So that computers exist is important for lots of the progress of science. In other cases that sort of instrumentation existed. I mean, I think things like, the discovery of quantum mechanics, probably associated with the fact that you could actually make precision measurements and you could have electronic amplifiers. These kinds of things are surprisingly driven by technology. I mean, I think it got figured out that, Einstein got to think about sort of simultaneity of clocks, because in Switzerland, where he lived at the time, everybody was obsessed with whether the trains would run on time and whether the clock at one train station was synchronized with the clock at another train station. So it's very common that these sort of ambient technological or world affairs kind of affect the things that get thought about. I mean, sometimes it's kind of charming because, things will be kind of brand names of their time. Like Turing talks about how, you could work this out with a Brunsviga. Well, we probably hadn't heard of those now. They were mechanical calculators. There's a lovely advertisement that I found for one which shows a Brunsviga in use in an airship as a kind of with a caption talking about modern times. Anyway, so let's see. Uh, I think we we probably should wrap up here, but okay, I'll take two more things here. Tarek is asking, do we need to incentivize scientists with financial compensation to get highly impactful results like AI? I I don't think so. I mean, I think that the correlation between kind of the sort of the financial motivation and the scientific intellectual motivation are not, they don't tend to be terribly closely aligned, and there are many. Uh, I'm trying to think of inventions that were made for money, so to speak, where where the invention got made because it was a thing that people could plainly see would be sort of financially successful. And I'm actually having a hard time. I'm thinking many counterexamples where people made inventions they didn't know that they would be valuable, and often the original inventors were not even the ones who benefited. I mean, that's a very common phenomenon. Certainly true in my life. There are many things I've invented where the financial benefit does not come back to me, so to speak. They were sort of ideas that got copied and other people have benefited and not the originator. And that's pretty common because sort of the machinery needed to commercialize something is not at all the same as the machinery needed to invent the thing in the first place. I mean, in my own life, I've been able to have a decent connection between some of the things I invent and some of the things that can be made commercially successful. That's very useful because it allows one to be freer to make other inventions, but that's not the typical case. Let's see. Ariana asks, how do other scientists and me regard scientific communicators, people like Carl Sagan, Brian Cox? Are they valued within the scientific community, and what do you think is their place in science and the history of science? It's an interesting question. I think that that's gone up and down. I mean, at the time when Carl Sagan was particularly out and about, he was not sort of, he wasn't, people just sort of pushed aside uh, scientists tended to push aside his kind of popularization, as they would call it. And it seemed like, you were either a popularizer or you were a scientist. You couldn't be both. Now, there certainly had been both. Charles Darwin was both, although he had, uh, he had his bulldog Huxley, who was more of a popularizer than Darwin was. But I think there started to be this kind of dichotomy between the explaining of science and the doing of science. Now, there was a period of time, particularly in the 1980s, when there were a whole series of sort of successful popular science books, so to speak. There had been ones earlier than that. But there was a time when there was a particular flowering of those kinds of books. I think, not in small part, the result of a literary agent named John Brockman, who went out selling science communication, science popularization books with wild abandon for a certain period of time. And I think it was at that time, why were people buying those books? The analysis that I certainly heard from editors in the publishing industry at that time was that it was like people would have been buying philosophy books, but the philosophy books by that time, the academic philosophy books, had become incomprehensible. And so they were buying books about things like cosmology, which sort of addressed the same philosophical issues, but in a more concrete way, more readily understandable. I think in modern times, I would say the last 10 years or so, particularly, maybe a little bit more than that, there's been more recognition among sort of the kind of academic scientists that science popularization has has a place, that it's needed in order to kind of sell the idea of doing science. I mean, this is something that, for example, NASA with the space program, they realized very early on you need artists to paint lovely space paintings and things like this to encourage, to communicate, to the public, why is this important? For example, in particle physics, that was a total fiasco, total disaster. Particle physics, there was a spending $10 billion on some particle accelerator. In the 1990s, there was this big push to build a superconducting, super collider, and this was, a $10 billion plus project, but the particle physics community did a hopeless job in communicating the importance of that to the general public. And eventually that project was killed, and particle physics sort of took quite a hit as a result of that. So I think people had understood, maybe actually partly as a result of that particular event, people understood, yes, it's important to communicate to the public why science is interesting and important, but it's still sort of a complicated mixture. I mean, when I wrote my book, New Kind of Science, I tried to do something kind of crazy. I tried to write a book that was both talking about a lot of new science and also a book that could be widely read by people and was accessible to people. I did that partly because my personal motivation was in part to be able to spread ideas and have other people be able to have the fun of understanding those ideas, but also because it wasn't going to, the ideas that I was trying to communicate was sort of foundational enough that it didn't really, there wasn't an existing fancy formalism that I could have used to describe these things. And so it was for even me to understand them myself, I wanted to explain them in sort of as sort of direct and simple terms kind of way as possible. But that caused lots of confusion with New Kind of Science, because people said, how can a book be both understandable and written for people to understand and be a book about sort of the frontiers of science? That was something particularly surprising to people in things like the physical sciences, not really surprising to people in other areas, because in other fields, when people have written about sort of general ideas about form, as people like architects have picked up, those kinds of books, whether it was Buckminster Fuller, whether it was other people writing about sort of the ideas of form, those books were sort of they didn't have technicality as such that sort of locked out the general public. I mean, I think this is again a phenomenon of kind of the excitement about specialization, the idea that there were sort of druids of science who could write things in these terms that were very sort of abstruse, and that sort of science was something that could only really happen in an incomprehensible way behind closed doors. That was sort of a vision, I would say, to some extent perpetuated by scientists, but certainly believed by the general public. And I think, in modern times, as I say, there's kind of this idea that the explaining of why one's doing science is important if you want to get the world to pay for the science you're doing. Also, in some of my own efforts, for example, of doing kind of open science and live streaming kind of the actual doing of science, that's sort of a thing where you're opening the closed doors, so to speak, and showing sort of the dynamics of what actually happens when science goes on. In terms of the place of sort of the exposition of science in the history of science, that's an interesting question. I mean, expositors of science, one has heard of some of them and not others. For example, in the 1800s, maybe Mary Somerville was a famous expositor of science. She was the translator of Laplace's Mécanique Céleste into English, and then wrote many other books. She was a well-known expositor of science. Then there were people like Michael Faraday, who was an expositor of science, but he's mostly known for his contributions to science itself. And I would say that there are other scientists known, people like George Gamow, for example, who was a successful physicist, but was also known for his kind of popularizations of science. I don't know, Mr. Tompkins goes to, I forget what the titles are, but those I think were notable in their time. But I think in the long view of history, look, in the long view of history, basically the ideas are the only things that really survive, and maybe the literary works. But I think these things which are sort of pure exposition rather than exposition for the sake of communicating a new idea, I think those are things that are of their time. And they're relevant for some number of decades, and then as the science advances, for example, and another thing to be said is that often when science is as science advances, you get to explain things in a different way. So, for example, when only a certain amount is known, sometimes I notice this all the time. When I haven't really figured stuff out, it's really hard to explain it. when I've really gotten to the bottom of something, suddenly it becomes easy to explain. And I think that's the thing that you see in sort of the history of science and science exposition a lot. All right, I think we should wrap up here. So for people on the live stream, thanks for joining us, and uh, bye for now.